All right. Good evening. Hey. Good morning, guys. I hope we are very fine. It's been a while. It's been a while. Last time we ended at binomial distribution. So let's continue our batons from that side. All right. So we completed binomial distributions. So we'll be able to formulate binomial questions and then answer them. Nice. So today we'll be talking about Poisson distribution. All right. All right. So you let me touch on this about binomial distribution. So they say if P, the probability of success is 0.5, which is it is half. The binomial distribution is symmetrical, and then it's what? A bell shape. So let me introduce myself again. I'm Nehemiah, but popularly known as Fearfully Ugly. So today I'll be taking you guys through probabilities. Today we'll be talking specifically Poisson distribution and hypergeometric distribution. So I just want to touch on this. So they say if the probability of success is 0.5, the binomial distribution is symmetrical and it's bell-shaped regardless of the sample size of n, which is regardless of the sample size. So this thing is really, really needed. So if you know this, and we are doing standard normal distributions, so you see that it's 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 this where you are like you are going to apply that knowledge. So when the value of p differs from 0.5, it is either in either direction, the binomial distribution is skewed. So normally we can say it is skewed to the right or to the left hand side. So the skewness is more pronounced when n is small and p approaches 0. So if p approaches 0, then we can say that it is skewed to the left. But when p approaches 1, then we can say that it is skewed to the right. So the binomial distribution, however, becomes more bell-shaped as n increases. So when the number of sizes increases, then the binomial distribution becomes bell-shaped. So let's talk about what we are going to do today, which is the Poisson distribution. So basically, if you really want to understand Poisson distribution, or if you want to know when to apply Poisson distribution, it's only the probability where, like, when you are giving a question to find a probability where time is related, or where you are finding a probability within an interval, within a fixed time, right? That's when we apply the Poisson distribution. So let's go through. Instead, when the total number of possible outcomes cannot be determined, the binomial distribution cannot be applied. So you see, binomial distribution is when the total numbers can be determined, right? But for Poisson distribution, when they cannot be determined, that's when we apply the Poisson distribution. So for example, we cannot count the number of potholes per mile. So if on the road, especially Ghana, we can count, for example, we can count the number of potholes per mile. So in Ghana, we can count the number of potholes, but we cannot count the number of non-potholes. So the number of non-potholes there, we cannot count because it is almost like a mileage or something. So we cannot count that. In such situations, we need a different kind of probability distribution to describe such natural phenomenon, right? So that's why we are coming to use the Poisson distribution. So explanation. So characteristics of Poisson distribution. So one of the characteristics, the outcome of interest are rare relative to the possible outcome. So the outcomes are rare relative to the possible outcomes, and then the average number of outcomes of interest per unit time or space interval is called lambda. So they use lambda to be the average, or let's say the mean divided by t. Is lambda. Is this? So the mean divided by t is the lambda. So that's what they are trying to say. The average number of outcomes of interest per unit time or space interval is called lambda. So mean is also the occurrences, the number of occurrences in an interval t. So for example, lambda times t. So lambda so that's what it is. Lambda times t is what we call the mean. When we find out the formula, we just be inserting. So the number of outcomes of interest are random, and the occurrences of one outcome does not influence the occurrences of another outcome of the interest. And then also the probability that an outcome of interest occur in a given segment is the same for all segments. So basically, these are the characteristics of the Poisson distribution. It's the Poisson is not difficult. It's not difficult. You just have to know the situation to apply it, and then you are true with it. So this is the Poisson distribution formula. So the probability of X happening is what we call the lambda t, which is the mean, as explained in the previous chapter. So no, previous page, sorry. So the mean raised to the power the x, right? And then this e is a natural logarithm something, and then minus the lambda t, which is the mean, all over the factorial of x. So is this same formula that they've simplified into this way. So you can use either this or this based on the question. Sometimes mean will be given in the question automatically. So if mean is given in the question automatically, then you apply this. But if mean is not given in the question, but let's say lambda is given and then t is given, then you apply this, right? So basically, this is it. So when lambda and t or the time is given, you apply this. But when the mean is given automatically, then you apply this formula. Let me change the color. So this red side, when lambda and then t is given, you apply this. But when only the mean, when the mean is given, then you apply this. So that's it. So as explaining. So in this formula, it's a where t is equal to the size of the segment of interest. say 2 hours. So t is the time, right? T is the time. And then x is the number of success in the segment of interest. So x is actually what we are looking for. You understand? The probability of x happening is what we are looking for. So the lambda is also the expected number of success in the segment, which is the lambda. So example, let's say maybe if a question is given, the time is given in 2 hours and we want to find the answer in 1 hour, for example. So the mean is also the u here. The u is then is the mean of the number of occurrences, which is the lambda times the t. Which is n1 hour, the number times the t is here. Okay, so they've even indicated it here. The mean is equal to lambda times t. So example, if u is equal to 20 per every 2 hours, then t is what? 2 hours, whilst lambda is 10. Remember the previous page, I made mention that if we want to find the mean, it's equal to lambda times t. So this lambda 10 times this 2 will give us the 20 here. Right. Yeah. So and then the e there is the base of natural logarithm system. So you can even punch it on a calculator. Normally, it's either you keep this thing in your head, or when you press alpha and then x10x below the calculator, you see where there's an answer, ans. So from the equal to sign to your left hand side, the ans is there, and then the key behind the ans, when you press alpha and that key, which is yes, this x, then this to the power x. So that is it. So when you press alpha and this key on your calculator, you will get sorry, you will get your e. You will get this e. So let's move on. So this is an example. So a study conducted at Whole Food Groceries shows that the average number of arrivals at the checkout section of the store per hour is 16. So you need to take into consideration the time very well, because Poisson deals with time. Once you see time in a probability question, then it is Poisson. So further, the distribution for the number of arrival is considered to be Poisson. They've stated it for us. Sometimes they will not. What is the probability of x equal to 12? So what's the probability that 12 customers will be arriving at the checkpoint in 1 hour? So if 16 comes in 1 hour, right? And we are also finding 12 in 1 hour, then we maintain our mean, right? We maintain it. But if it were to be different, like let's say we using 12 people in 30 minutes, then now we need to what? Divide the hour by 2, right? And then get our t. So in this information given, the mean is equal to the lambda t, which is it. So 16 times 1, which is this 16 times the 1 hour will give us our what? Our mean. It's already there. So we just put it inside. Please, it's not inside what you are thinking. We are putting it inside this formula. We are putting it inside this formula, sorry. So basically, this 16 is our mean. Oh, This 16 is our mean. And then the 12 is the X, which is the number of customers. And then this E is the one, the natural logarithm, whatever. And then this is the negative mean again. We are just putting everything back into the formula again. And then all over the X factorial, which is the number of this in factorial. So when you punch all this on your calculator, this is what you'll be getting. It's so simple. Once you remember the formula, remember that in exams, the formulas will be given. The formulas will be given. So, okay, I don't know whether Poisson, but most often they give us the tough formulas, but the easy ones, I don't know. So this is another example. Patients arrive at the emergency room of Mercy Hospital at the average rate of 6 per hour on weekend evenings. What is the probability of 4 arriving in 30 minutes on a weekend evening? So now they are telling us that 6 arrives at what? And per hour, right? So what is the probability of 4 arriving at 30 minutes? So this is when we divide the hour by 2. So look at what they've done here. So now our lambda t, or our mean, will be what? 3 per minute. So we divide lambda, now 30 minutes divided by 60 divided by 30 is 2. So now we divide our mean by 2, right? And then we get what? 3 per minute, 3 per 30 minutes, sorry. So now we are looking for this 4 in, so we just put the same thing in the formula, as the formula is U, sorry, U raised to the power X, E raised to the power negative U all over X factorial. So basically, the U raised to the power S will be multiplying the E, right, raised to the power negative U all over the X factorial. So the same thing is what they place in here. The same thing here. And then, right, things are going well here. The same thing. So basically, they are telling us the Poisson mean is equal to lambda times theta, one we know. The variance and the standard deviation. So the variance is the standard deviation squared. So the root of the standard deviation, the root of the mean is the standard deviation, where y is the number of, so that's the lambda, and then t is the thing. So we can also use the Poisson table, but the Poisson table, normally the coefficients are given. So for example, lambda t. So they give us that x in this particular table that they've given, x is equal to 2, right? Since x, you locate x equal to 2 here, right, as you can see from here. And then the lambda is 0.5. So we locate it 0.5 here, right? So that's what they've also done here. So this will be the probability of it happening. Since here's the probability. So once we solve everything, this is what you're going to get. So if x is 2 and then the lambda is 0.5, this is the probability. So that's basically it. So they say that t is 100, but t is not being located. Like we know that lambda t is the mean. So this one times this will give us, I think, Z5. Z5. So basically, they will give you lambda t. So I'm sure here, I'm sure this is a mistake. I'm sure the t here is supposed to be 10. Because when you multiply, the t here is supposed to be 10. Because when you multiply this 100 by this, you get 5. But they said that the 10 is 0.5. So unless you multiply this one by 10 before you get 0.5. So I think that there is a mistake in here. So this is supposed to be 5. It is supposed, the t is supposed to be 10. The t is supposed to be 10 because lambda t is the mean. So if lambda t, then it's supposed to be 10 times this one. Yeah. So look at it here. So it's supposed to be 10, not 100. Supposed to be 10, not 100. So that's basically. Just that this one looks more faster. When you're using the Poisson distribution table, it looks more faster and easier and better and fresher. So let's move on to, I wish, okay, I'll find an example and I will solve together. So let's go to the hypergeometric distribution. So n trials, number of trials in a sample taken from an infinite population of size n. So which is the sample size, the sample population is taken from a bigger population, right? So the small n is for sample population, and then the big N is for the big population. So a sample taken without replacement. So if something is taken without replacement, then it means that the thing has spore or it has like something that will not be retained. So you see that's I say defective or something like that. So trials are dependent and then concerned with the table concerned with finding the probability of the sample success in the sample where x are where there are x, so where there are populations and the big S is the population success in the population. So let's move on. You understand. So this is the hypergeometric formula. It's easy. It's easy. You just have to know the combination of the population size, which is the real population size, right? And then the subtracted from the number of success, right, in the bigger population in the population size. And then this one is a sample size. Sample size. This one is a sample size. And then this one is the, so you subtract it from the success of the sample size, right? The success in the sample size. And then you multiply it by the combination of the number of success in the population and then the number of success in the sample size all over the combination of the number of the population size and then the sample size. So basically you just, I'm sure they will give us this formula in the exams, and then if in case there's a question, and then you just have to punch in, you just have to know that the big N is the population size, the small n is the sample size, the big X is the success in the population size, and then small x is the success in the sample size, right? And then the same thing is, so we just know them and then you just punch them in there. So what I've realized so far is that apart from the formulating of the word problems and stuffs, Quantity is basically formulas. So, okay, so let's see. They say where n is the population size, x is the number of success in the population, n is the sample size, x is the small x is the number of success in the sample, and then n minus x is the number of failure. Yeah, since x is the success, then n minus x should be the distance. So they gave us an example here. Light bulbs were selected. Three light bulbs were selected from 10, right? Out of 10 light bulbs, they selected 3. Of the 10, there were 4 defectives. So meaning that the 10 that was there were already 4 defectives in it, right? So there were 4 defective already in the 10 bulbs before they took 3. So what is the probability that 2 of the 3 selected are defective? So we are selecting the sample size, the sample. So the probability of 2, right, is the x, the small x here, which is the success. And then we are selecting 3. So the sample is what? The 3. The sample size is the 3. And then the total bulb is what? Is 10. And then the defective one, and as the success in it is what? The success of reselecting the defective is 4. So we put in the same thing. So we put in the same thing, 10 minus 4 will give us 6. And then 4 minus 3 will give us this one. And then this 4 is here, which is the success of the sample. And then success of the success of the population. So the defective, then the success of the sample is this one, right? So it's basically you putting the formulas in there. Just know where you put it, and then you are done. So this has brought us to the end of the probability distribution, the normal one. So in the next session, we'll talk about the normal distribution. So I'll do another video, maybe tomorrow, probably solving, because I can't see questions. I can't see more questions in this slide. So I will solve different questions. I'll project a question, then I'll solve it, and then after that, I'll give an assignment, right? So take care, take good care of yourself. See you tomorrow. Bye.